All right, scholars, so we're going to go ahead and move along with our unit on rotation and talk about really the meat of this unit, which is basically reanalyzing everything we've done so far in this entire course. We've already done kinematics, we've talked about inertia, and so of course what we have to talk about next are Newton's laws of motion, so forces, dynamics and statics and things. And then energy, and then momentum. We're just going to recapitulate the entire course for rotating objects. And the backbone of this is going to be a concept known as torque. So I suppose if we wanted to be organized and really think through what we're doing here, we're trying to relate everything we've done in the course to rotation now. We've seen what Newton's laws are like. We've seen what energy is like. We've seen how momentum works for objects moving in straight lines, objects with translational motion. We now want to go back and review all of that for objects that have rotational or possible rotational motion, objects that may rotate. Really, whenever you have an object of shape, sometimes we call them extended objects, extended rigid bodies. They have a potential to rotate relative to some axis of rotation. In other words, in this class, we've been treating all of our objects as if they're just little point particles, and we didn't really care about the shape or the size of the point particle. We just worried about how those particles interacted. Now, though, we are going to care about the shape and the size of the object. The shape and the size matters because it's going to affect how the object could potentially rotate. Okay, so everything we're going to discuss is applicable when the object is extended, when it has a shape. Okay, so first we need to analyze, I guess, Newton's laws for objects of shape. And the backbone of this concept, as I said, will be something known as torque. So let's define what torque is, first of all, conceptually. Torque is the rotational analog to force. So think about what this means. Forces can do what? They may cause translational acceleration. Think about Newton's laws, right? Newton's first law, in order to cause something to accelerate, you need a force. Newton's second law, that resulting acceleration, in order to cause something to accelerate, you need a net overall unbalanced force. Newton's second law says that the resulting acceleration will be proportional to the force and inversely proportional to the inertia or the mass of the object. Sigma F equals ma. And Newton's third law says, of course, that forces come in pairs. If object A pushes on object B pushes back in the opposite direction with the same size of force back onto object A. So forces may cause translational acceleration. They could cause an object to change its motion, either the direction of the motion or the speed of the motion, to change its velocity. Well, in the exact same way, torques may cause objects to change their rotational motion. They may cause rotational acceleration. And that, of course, is denoted with the Greek letter alpha. So let me remind you that omega is an angle change with respect to time of a rotating body. And alpha is the change in omega. It is the rotational acceleration. Omega is rotational velocity. Alpha is rotational acceleration. How is the velocity changing? Well, every object that's rotating will have an omega. And what I'm saying now is that in order to cause an object to change how it's rotating, to speed up or slow down, or even to begin rotating, if its initial angular velocity was 0, there has to be a torque. acting on it. Just like in order for something to speed up, slow down, change direction, there has to be some interaction, some push or pull, a force to cause that translational acceleration. Same exact thing for rotational. There has to be a torque acting on the object, okay? It is the rotational analogy to force, okay? So let's define torque now mathematically. This is the Greek letter tau. That is, it just looks like a fancy T, right? That is the abbreviation for torque. Torque is equal to, and it is a vector, it is equal to the cross product of these two vectors, r cross f. Now, let's talk about real quick what a cross product is. Hopefully you remember the two types of vector products. One of them is a dot product. Who can remember where dot product showed up? Dot products, what I'm going to write down here is just kind of a review. You don't need to write it down, just please watch. One important dot product we have in this course is work, right? Work, we said, is the dot product of force and displacement. So, simplest example, the one I always use, here's a box, you're pulling it at some force up at an angle, and as a result, you get the thing to displace delta x. If we want to know what the final kinetic energy is, what the change in energy in this object has been, where that is equal to work, you are applying an external force, so you are doing external work to increase the kinetic energy of this object, then we're not worried about what the force is that you applied, but only the component of the force that actually helped the thing move in that direction. So we would say that work then is this. We would draw those two vectors tail to tail. There's my force vector. Here's the displacement vector. And there's the angle of the angle between the two vectors, where I would say that work is the component of force that lies parallel to that displacement, the force that has caused that displacement, where I only want the parallel component of force. Well, how am I going to find the magnitude or the size of the force that is in this direction? In other words, what is the x direction of the magnitude of the force in the x direction? Well, of course, I'm going to take my force and modify it by a factor of cosine theta. So work then I would say is F cosine theta. That gets me the component of force acting along this, this line here, and multiplied by the other vector delta x. So really it's F delta x cosine theta. That's the dot product, and a dot product, the result of that is a scalar. Work is, just a positive or negative value. Either we add energy or we take energy away from the system. So work as a dot product, and all dot products are going to end up being exactly like this, where you multiply the size of the two vectors and then you modify that by multiplying the cosine of the angle between them whenever you draw the two vectors tail to tail. That is a dot product. It gives you a scalar result. Let's talk about what a cross product is and what this equation means. Cross products are a little bit wackier. This time we are not worried about the components of the vectors that lie along each other, but the components of the vectors that lie perpendicular to each other. So in order to do this, really the best way for me is to give an example. So let's say that you go over to your door, and you push on the door, and that causes the door to rotate. What you've done is just applied a torque to the door. So I'm going to draw a top-down view of the door, and here are the hinges over here. So there's my axis of rotation. big hint, I'm going to be saying this over and over again, whenever you're solving these rotational problems, the first thing you have got to do is define the axis of rotation. So there's my axis of rotation, that's like the hinges. And again, this is a top view of the door. And let's say that you're on this side of the door and you apply a force by pushing the door this way. So there's your hand pushing on the door. So I would call this like the point of contact or something. That is where the force is contacting the door. And so I can draw a free body diagram just like this. And I can say, boom, there's my force. That is the contact force acting on the point of contact, just like that, right? Simple enough. So, of course, that's going to be our force vector in this equation. Let's talk about what this r vector is. That r vector, and you'll see it written in different ways. It could be an s sometimes. That is just a distance, a position vector, or sometimes you can think about it as a displacement vector. This is the most complicated and the most important part of this equation, so listen carefully. Where that r vector is a position vector from the axis of rotation to the point of contact of the force. So my r vector is right here, and it has a length of r. It is a vector. Really, we're only worried about the length of the thing. But it is indeed a vector because you're about to see that the direction matters. So it's drawn from the axis of rotation toward the point of contact, just like that. So now that we've identified our vectors, we can talk about how to do the cross product. The cross product is going to be just like this, and there are several different ways that we can think about it. I'll show you multiple ways. The first way that I prefer to think about it is to draw both the vectors, again, tail to tail. So there's my r vector, and then here is my force vector, just like that. I'm going to identify then the angle between the two vectors. There it is. And this time I'm going to, last time when I did a dot product, I was worried about the cosine of that angle. That gave me the component of one vector that lies along the other vector. This time I'm going to take the sine of that angle, because taking the sine of that angle will give me the component that lies perpendicular, the component of the force that lies perpendicular to this r vector. The reason for that is that I'm interested in what's causing the rotation, and to cause rotation I'm always going to have to apply a force that has some perpendicular component to a line drawn, to this position vector drawn from the axis of rotation to the point of application of my force. In other words, it's no mystery that if I were to come up to my door and apply a force this way, parallel to this r vector, parallel to a vector drawn from the point of application to the axis of rotation, nothing's going to happen, right? I have to apply a force that is tangent to a circular path to cause the thing to rotate, to cause the thing to change its rotational motion. So, and in fact, this makes perfect sense, because if this was my force, let's call it F prime or something, if this was a new force I came in and gave, if I were to draw, these two tail to tail, the angle between them would be 0. The sine of 0 is 0, so there would be no torque there. When is torque at a maximum? When does this equation reach a maximum? When my angle is 90 degrees, right? So I get my maximum torque. It's important to think about this a little bit conceptual. I get my maximum torque whenever I push perfectly perpendicular onto the object. Now, I think that you are probably safest to, whenever you're solving for torque, to redraw them tail to tail like this, redraw your vectors tail to tail. But geometrically speaking, it really doesn't matter. We just want the angle between the two vectors. And you could certainly, over here in this diagram, you could certainly take this angle. that angle between the vectors when they're not drawn tail to tail, and you're going to get the same result, right? So let's do some quick geometry. So that angle that I just drew over here would show up in this diagram right here, and that would be equal to 180 minus theta. And of course, the sine of theta and the sine of 180 minus theta are always going to be exactly the same. So we are justified in just taking this angle theta right here, and we would get the exact same result. I prefer to draw them tail to tail because later you can do some other things with that, but it really doesn't matter, whatever you're comfortable with. Okay, so this diagram, actually, if I do take just that angle, the angle right here, I think that the sine idea jumps out at you a little bit more. I'm looking for the component of the force that is perpendicular to this vector. So F sine theta would get me this, which is going to be the tangential component of the force. The component of the force that lies perpendicular to this other vector, okay? And please remember what this other vector is. It is a position vector drawn from the axis of rotation to the point of application of the force. All right, so that is how you calculate torque. Now, let me talk to you about the fact that this is a cross product, and cross products always give you a vector result. The cross product of two vectors is another vector, and we know that vectors have directions, don't we? So we need to talk about directionality with this. How can we determine the direction of this torque vector? It's a little bit weird, it's a little bit funky, but here's the idea. Whenever you do a cross product, your answer, the result of that cross product, that vector, will have a direction that is perpendicular to both of these vectors. Here's what I mean by that. My force and my position vector are in the plane of the page right now. They are flat. So how can I have a resultant that is perpendicular to both of them? Well, the torque vector is going to have to lie in another plane. It's going to have to be coming out at me towards me from the screen, away from the screen, or in away from me into the screen. The result of a cross product will always lie in a plane that is perpendicular to the other two vectors. I know that's a bit funky, but that is the way that it works. There's a good reason for this. The reason is that torque, therefore, will always lie along the axis of rotation. So my axis of rotation right now, because this is a top view, is going like into and out of the page, right? It's a three-dimensional axis coming into the page or out of the page at me. Torque will always lie along that. The reason why it's convenient to denote torque with a direction that lies along the axis of rotation is because that does not change. However, as I push this door around, the direction of force, the direction of R, those things are changing. They're spinning with respect to the axis of rotation. But guess what is not changing? The axis of rotation itself. So by grounding the direction of torque with the axis of rotation, it makes my life a lot easier. I can just say that, yeah, my torque lies along the axis of rotation out at me, or I can say, yeah, my torque lies along the axis of rotation down into the page away from me. So those are your two options. And here is how you can figure it out. You can use something that is known as the right hand rule. Here's how this works. I will try my best to explain it, and then I'll give you a little video of my hand actually doing it. So the right hand rule is this. You take your right hand, and you're going to take your fingers, not your thumb, your fingers of your right hand, and point them from the axis of rotation, point them in the direction of R. So remember what R was, how we defined it? It was from the axis of rotation to the point of application of the force. So I'm going to take my right hand right now and point it to kind of turn it so that the fingers of my right hand are pointing to the right along the screen, to the right of my laptop. Okay. And then I'm going to rotate my palm around, rotate my wrist, so that I can curl those fingers in the direction that the force is pointing. So in other words, my force, and I can use either diagram. It doesn't matter which diagram I use. This one's probably, this one's probably a little bit easier, but it really truly does not matter. I have my fingers of my right hand pointing to the right, and I'm going to twist my palm and my wrist around so that when I close up my fingers to make a fist, I'm not moving my thumb at all. My thumb is pointing like straight out, like it's making an L with my other fingers. When I curl those fingers, I move my wrist and my palm such that those fingers curl in the direction that the force is pointing. So right now, my wrist is, I'm kind of turning my arm awkwardly. My palm is pointing down to the keyboard of my laptop. My fingers of my right hand are pointing to the right of the screen. I do that because when I curl my fingers, then they're curling around into the direction that the force is going. So my fingers are curling around clockwise, down and to the left. And when I do that, my thumb is pointing into the screen. My thumb is giving me right now the direction of the torque. So torque is always going to be along the axis of rotation, perpendicular to both the r and the f vector. And it's either going to be pointing away from you or pointing towards you, basically. It's going to be pointing down the axis of rotation or up the axis of rotation. My thumb is pointing down the axis of rotation right now. It's pointing down into the screen. Excuse me, it's pointing straight out away from me into the screen. So that tells me the direction of the torque. So for this little example problem, I would say this. I would say that the torque vector, so I can calculate its magnitude with this little equation, where again that angle is always the angle between the two vectors, either drawn like this or this, tail to tail. And the direction, I use the right hand rule, point my right hand fingers in the direction of R away from the axis of rotation to the point of application of the force, that's to the right. Rotate my palm and my wrist such that I can curl those fingers around towards the force, in the direction that the force is going. That leaves my thumb pointing straight into the screen. So I would say that the torque direction then is into the screen. And we define that as a negative value for torque. If you're going into the paper or into the screen, we say that's negative. Another way of saying this would be that my torque lies along the negative axis of rotation. Okay? This makes pretty good sense because of the following. If you actually go push on your door like this, you're going to start your door rotating this way. You're going to give it angular acceleration that way. That is counterclockwise. And remember, with rotation, we always say counterclockwise rotation is negative. So my negative torque is causing a negative angular acceleration. Does that make sense? In fact, I failed to mention this earlier, but angular velocity and angular acceleration, those are both vectors, right? I just talked about them briefly as, clockwise, counterclockwise, etc. But they also follow the right-hand rule. Really, truly, we define their direction as being positive or negative along the axis of rotation. You use the exact same right-hand rule to do this. We always say that that counterclockwise is positive, and clockwise, of course, is negative. The reason for that comes from the unit circle, right? When you're going counterclockwise this way in the unit circle, your angle gets bigger. But the positive and negative of omega and alpha really correspond to the positive and negative axis of rotation. Again, we like to anchor our directionality on the axis of rotation because it doesn't change, it doesn't move. All right. Okay, so I just have thrown a lot at you, but hopefully you kind of get the idea of a cross product. You get the idea that the cross product magnitude collapses into this. We're worried about the sign of the angle between the two vectors, and then the direction we use the right hand rule, and it's going to be along the axis of rotation somewhere, either down it or up it. Along the positive or along the negative axis of rotation. Here in this example, my thumb was pointing into the screen, so I say that's along the negative axis of rotation. Okay, if I wanted to draw the torque here, how do I draw something that's going into the screen? Well, I can do this. I can put a little circle, draw an X in that circle, and that is my torque vector. That X represents it going into the screen away from me. It's like you've shot an arrow, and what you see as the arrow leaves you is the tail feathers of the arrow. That's how I remember it. What if torque is coming out at you? Well, then you would draw that, a little circle with a dot in the middle, and that's like an arrow with the point coming at you. So you see that point approaching you. That would be coming out of the screen. That would be positive. Ours, of course, is negative going into the screen. Okay, so this is the definition of torque. Maybe we should do a couple more examples. Okay, let's say that we have a rod or something. It could be a meter stick, something like that, and its axis of rotation is right here. And we're applying a force. We're pushing it down this way. So here's the point of application of the force, and there's my force vector. I want to know which way is the torque pointing. So the first thing we have to do is remember what torque is. It is the cross product of R cross F. So we need to determine what these two vectors are. Remember that the R vector is drawn from the axis of rotation to the point of application of the force right here. So there's my R vector. And let's write an expression for the magnitude of that. I like to draw my vectors tail to tail. There's the angle between them. I'm looking for this component of the force, the tangential component, the force that lies tangential or perpendicular to the R vector. And so, of course, to get that, I need to manipulate force by a factor of sine theta. So it becomes FR sine theta. Remember that you could also choose to use this angle here. Let's see real quick where that angle shows up in my diagram. Where here's the angle that I'm calling theta right there. And so, of course, those are going to be, what is that, complementary to each other. So this angle here would be 180 minus theta. And of course, the sign of those two are the same, so it really truly does not matter. Okay, let's figure out the direction of the torque now. This is the important bit. So my right hand is going to be pointing to the right. My finger is along this R vector from the axis of rotation to the point of application of the force. I need to pivot my wrist and my palm so that my fingers point down towards the F vector, down towards the force vector, and that has my thumb pointing into the screen. So once again, in this example, we have a torque that is pointing in the negative axis of rotation direction. In other words, that is into the page or into the screen. And if I wanted to draw it up here, I would draw it just like that with an X in a circle to denote that my torque is going into the page. All right, another one. Let's say that we have this object here. Let's say that this is the axis of rotation. And let's say I'm pushing on this side of it, and I'm pushing out this way, just like that. So there's my force vector. Torque, cross product of R cross F. Here's my R vector from axis of rotation to the point of application of the force. Here's the angle between them. I could do it that way. I could also now draw them tail to tail. Here's my r vector. Here's the force vector. I've drawn them tail to tail. Here's the angle between them. So that, of course, ends up becoming FR sine theta. Let's think about the direction now. Take the fingers of my right hand. This time they're going to point left. And I have got to figure out how I can pivot my palm to curl my fingers up and around, kind of wrapping up and around to the right, so that, because that's the direction that my force is going. It's going up, so I need to curl my fingers up. And when I do that, I have to pivot my palm kind of awkwardly, and I can see once again that the torque is into the screen. What does that mean? That means that my torque lies along the negative axis of rotation. And I could denote that just like this once again. Okay, let's say that this time we're pushing on the other side of this object, and let's say that we push, maybe this way. Gotta draw my r vector, my position vector that goes from the axis of rotation to the point of application of the force. Torque is, of course, the cross product of r cross f, which of course will, here's the angle between them, or I could draw it tail to tail. Hopefully you guys are getting the hang of this. There's the angle between them there. Whichever angle I use doesn't matter. I'm going to get FR sine of theta. Once again, if we want to check the geometry on that, this angle right here would show up right here, and of course that's just 180 minus, and the sine values are the same for those. And now let's think about direction. This is what we really want to practice. Doesn't matter which diagram I pick, but I'm going to point my fingers of my right hand to the left, because that is the direction that R is pointing in. And this time I'm going to wrap them kind of down, because the force is going down. And when I do that, my thumb is pointing out at me. So therefore I would say that my torque is along the positive axis of rotation, or out of the page. I wanted to label that on my diagram, circle with a dot in it, and there's my torque. Now, this makes sense once again that my torque is along the positive axis of rotation, because what is this going to cause? This is going to cause the door to start, or the meter stick to start swinging this way. So this thing will start to rotate like this, and of course that goes with the unit circle. The angle is going to get bigger and bigger and bigger. So it makes sense that is defined as positive. Okay, let's do one more example. Let's say this time that the axis of rotation is like this. So this thing is capable of like swinging into the screen or coming out of the screen at me. And let's say that I apply a force right here. And let's say that my force is going into the page. And here's my r vector. So my force is perfectly into the page, and we know that torque is worried about the sine of the angle between R and F, but if F is going directly into the page, that's 90 degrees, right? That's perfectly perpendicular here. So the sine of 90 is 1. So the magnitude of my torque is just FR. And what direction is torque pointing in? So once again, right hand rule. Point my fingers to the right, curl my fingers in toward the screen, because that's the direction that force is going. That causes my thumb to point up. So I can actually draw my torque vector now. My torque vector is pointing up. That, of course, is going to correspond to a positive axis of rotation, because my axis of rotation this time is actually, I can see it, it is on the plane of the screen. And my torque vector would then be pointing up it just like that. Okay, so 3 things you guys really need to know. Conceptually, what torque is. Mathematically, how to calculate the cross product. and then using the right hand rule, how to determine the direction of torque. Remember that torque is the analog of force. It is the ability to cause a change in rotational motion, just like forces cause changes in translational motion. Next, we're going to talk about how torque does that. We know that according to Newton's second law, sigma F equals ma. A net force will cause acceleration proportional to mass, inversely proportional to mass. Torque, in the exact same way, a net torque is going to cause rotational acceleration. And what do you think it's going to be inversely proportional to? What is the rotational analog of mass? Rotational inertia, or moment of inertia, right? So that I value that we've spent a long time calculating. So this is Newton's second law for rotation. And notice that there's a one-to-one correspondence. The rotational analog of force is torque. The rotational analog of acceleration is a rotational or angular acceleration. Rotational analog of mass is rotational inertia that we've spent a long time calculating. Okay, so these types of problems are going to work exactly the same as our old Newton's law problems. It's just that this time we're going to be worried about the shape of the object. We don't just deal now with point particles, we deal with objects of shape, extended objects that have a shape. And we're worried about where the force is being applied and in what angle the force is being applied, because that is going to affect what the torque is. We're worried about how the mass is distributed along that object. That's going to affect the rotational inertia. All right. But really, these types of questions involving torque and seeing how different torques cause different types of angular acceleration, they're going to work exactly the same. You're going to be drawing free body diagrams where the forces are going to be acting at some location on the object, just exactly the same. All right. So next we're going to practice this and do several example problems, and hopefully you guys will get the idea with torque. All right. Okay, so let's do an example for torque. Let's say that, that is kind of a weird drawing, but let's say that there is a really stubborn bolt that you're trying to loosen with a wrench. So here's the bolt. It's coming out at you, out of the screen. Here's the wrench. Just like this, and this thing is really stuck. So what you do is you get a really long wrench and you apply a really big force to the end of it by standing on it. You're like jumping up and down, standing on this thing, trying to get the bolt to budge. That supplies a force of 900 newtons over here, and the long wrench is 0.8 meters away from the bolt. Now remember, the first thing that we always need to do to analyze torque and rotation is think about the axis of rotation. Well, the axis of rotation is going to be the bolt itself, like coming out at you towards you from the screen right now and going into the screen. So that's the axis of rotation. So let's try to figure out what the torque is going to be. So I know that torque is given as a cross product of R and F. So I know the size of these things. The size of F is 900. The size of R, maybe it would be helpful if I drew R. I always like to draw all over my diagrams. R is here, and that of course is 0.8 meters, just like that. To do the cross product, it's going to collapse down into RF sine theta. So what I need to do now is try to figure out the sine of the angle between them. You know that I like to draw them tail to tail to do this. So here's my R vector. Here's my F vector. And I know that R is like up at an angle of 19 degrees away from the horizontal. So therefore, this whole angle right here must be 109 degrees. This is 90. So 90 plus 19 gets you 109. So now my equation becomes 900 times 0.8 times, whoops, I kind of labeled that. This whole angle here is 109 times the sine of 109. And that's going to give me my torque. Make sure that you're in degrees. Sometimes we do use radians for rotation, but I'm measuring the angle between these vectors in degrees. So 900 times 0.8 times the sine of 109. That gets me about 681. Now, here's something we have not talked about, which is what units do we use for torque? It's going to be quite simple. The units are going to be the units of force times the units of position. So Newton meters. Newtons times meters. Now, I need to take a moment to talk clearly about this, this unit and make sure that everyone is on the same page. We've seen newtons times meters somewhere else. That is one way to define a joule. Remember what work is defined as? Work is defined as a force applied over a distance, causing a change in energy. And the general equation was F dot delta X, where we literally just multiply newtons times meters. And that gave us the unit of joules, where joules is energy. Okay? Please do not get this Newton meter confused with this Newton meter. Okay? A joule is indeed the energy content that results from applying 1 Newton of force over 1 meter of distance. Where that's work, that's a completely different concept from torque. Torque is a cross product. Okay, torque is not work. It is not a change in energy. It is just like a force. Okay, it just so happens to have this unit of Newton meters, newtons times meters, because it's the cross product of a position vector and a force vector. So please, please, please do not get this confused. All right. I want you to notice one thing that we've not really talked about. Conceptually, it's going to be important for you to know like how to compare different torques on an object. Well, the longer the r vector is, obviously the bigger the torque will be. This is why if you go up to your door right now and you try to push it closed, so let's say here's your door, this is a top view. Let's say here's the axis of rotation. If you apply a force here and then apply a force here, which one is going to result in a more rotation of the door? Which one is going to more easily rotate the door? It's going to be F2 because it's a farther distance away from the axis of rotation. That's what this r vector is in the torque equation. So that's why we have meters in there, because torque does depend on this position vector. Where is that force being applied on the extended object? That does indeed matter. And the farther out we are, the bigger our torque will be. And then remember that torque is also adjusted by this sine. The larger the sine value, the greater the torque will be. Please remember that sine gets bigger as you get to 90 degrees and then gets smaller as you get away from 90 degrees. So if a force is already perpendicular, like in this case, my forces here are perfectly perpendicular to that r vector, then that's going to be the maximum torque I can get, right? My sine of 90 will be 1, and so I will not have a fraction here that I will have to adjust this by. So please understand this conceptually. This is a pretty simple torque problem. Let's get into a little bit more complicated. Actually, I take that back. This one is not super complicated, but I just want to show you that just like we can draw a free body diagram to represent different forces on a point particle, and think about Newton's second law in terms of the net force or the sum of the forces, we can do the exact same thing for torque. So let's say that I have some blobject. It's a thick blobject. Let's say that I have some blobject like this, and here is the axis of rotation. And let's say that I have two forces that are being applied. Force 2 over here, force 1 right here. And I want to know, what is the net torque? What is the overall torque on this object? Well, just like forces, you just add them up. You just find each torque and add them up, and that's going to be the net torque. For objects and their rotation, it is not just torque that matters, but it's the net torque that matters. Remember, Newton's second law is not just F equals ma, but sigma F, or sum of, or net force, equals ma. And for rotation, it's the exact same thing. It's going to be the sum of the torques, the net torque, that ends up mattering for the rotation of the object, all right? So it will always be important to find the net torque acting on an object. So the first thing I need to do is define the axis of rotation. I've already done that. Then I need to draw some vectors, some r vectors, away from the axis of rotation to the point of application of the forces. I'll say that's r1. I'll say this is r2. This is really the only thing that we're adding in this free body diagram. Before, we had, just point particles and forces acting on that point particle. Now, though, we have forces acting at some position. So you always have to think about the position vector from the point of application of the force to the axis of rotation. All right. And then, of course, we're going to have an angle between them. If I were to kind of redraw force 1 tail to tail, it would be right here. This is just me figuring out the angle between them. So I could say, like, this is force 1. And then here's the angle right here. And that would also show up right here. Does everyone see that these are the same angles? So I can call this angle 1. Same exact thing over here. This would be angle 2. All right. And so my net torque is going to be torque 1 plus torque 2, where torque 1 over here is going to be F1 R1 sine of theta 1. Torque 2 is going to be F2 R2 sine of theta 2. Right? And yeah, we could have called this theta 2 or this theta 1 the angle between them. But again, I kind of like to think about the angle when I draw them, the vectors tail to tail like this. It really doesn't matter. So is this going to be my answer? Yes, but actually no, because remember that direction matters, right? These are vectors. So I have got to think about whether these vectors are going to help each other or whether they're going to hinder each other. So what do you guys think? I mean, look at the way these forces are. This force is trying to cause the object to rotate around this way, right? And this force giving rise to this torque 2 over here is trying to get this object to rotate around this way. So those are opposing each other. Those are two different rotational directions. This one wants to be clockwise, negative. This one wants to be counterclockwise, positive. So I can think about it just like that, this force would cause a counterclockwise rotation, so it's positive. This force will cause a clockwise rotation, so its torque is negative. So I could call this a negative torque. I could also use the right-hand rule. So thinking about this over here, when I do that, and I use the right-hand rule, for torque 1, my thumb is pointing out of the page towards me. That's a positive torque. For torque 2, my thumb is pointing into the screen away from me. That's a negative torque. So you have got to pause and think about direction, and it's not going to be immediately clear to you what's going to be positive, what's going to be negative. So my final answer ends up being F1 R1 sine theta 1 minus F2 R2 sine theta 2. They're opposing each other. They're working against each other. I need to call this one negative because it's trying to cause negative rotation. Okay, so please remember that directionality matters. Okay, let's say that I have this scenario where I have this pulley and it has a cord wrapped around it, and dangling from one free end is a block of mass little m. So let me just define some variables for us. Let's say that the mass of the pulley, big M, is 2.5 kilograms. Let's say that the radius of the pulley is 20 centimeters. Let's get that into meters right away, 0.2 meters. Let's say that the little mass, little m, is 1.2 kilograms. Just like that. And let's try to find some things that, that would be interesting. I want to find the acceleration of little m. I want to know the angular acceleration of big M. How quickly is this thing going to be changing its rotation? I want to know the tension force in the cable right here. Okay? Some important things to note. Let's say that this thing is rotating on an axle at its center. I haven't drawn it very well. Let's say there's no frictional interactions there. And let's say that the cord does not slip on the pulley. We'll talk about what that means later. But basically, all the motion is proportional. Okay? All right. So this is really an important type of problem, because you're noticing that we've already done pulley questions in the past, but now it's more complicated because this pulley is an object in my system that can rotate, that can spin. Okay, I'm gonna have to draw free body diagrams for both objects. All right, so the block little m, I have force of gravity, which of course is going to equal little mg, and I have a tension force. That's one thing I want to find. I need to draw a free body diagram for my pulley, and this time the shape matters. This is an extended object that is going to be rotating. So let's think about the forces that matter. I could draw the force of gravity on it right now. Really important for you to note, the force of gravity always acts on the center of mass of the object. I'm assuming that this thing has mass that's evenly distributed, so the force of gravity will act at its center. And this thing is being held up by the axle, so that's like a normal force. Those cancel each other out. Of course, the whole pulley as itself has no translational motion. There's no net force acting on the pulley's center of mass. But there is another force acting on the pulley. Can anyone determine what it might be? It is a force of tension acting right here. So I want you to think about this. If the tension force on this mass goes up this way, there's got to be a Newton's third law pair to that. That tension force has to pull down on something else, and it's going to pull down on this pulley. So here's my tension force, and it's going to be the same as this tension force on this mass. Now, I look at this and I can see right away that there's a torque involved, because I have a force that is located at some distance away from the axis of rotation. Here's the axis of rotation of the pulley, and this force is located at a distance r, right? The radius of the pulley. So I know right away it's going to provide a torque to cause the pulley to have an angular acceleration. So here's my r vector. What is the angle between those two vectors? That's a 90-degree angle, isn't it? So this is quite simple. So I can write now Newton's second law expressions. For this object, I'm going to have to write a torque expression. Torque is going to be equal to R cross F, which is R ft sine theta, where that theta is the angle between those two vectors. Remember what the r vector is. It's the position vector from the point of application of the force to the axis of rotation. Well, theta is 90 degrees, the angle between the two vectors, so sine theta is just 1. So that's going to equal r times ft. That's what my torque equals, okay? Now I can write another expression for that, right? I know that net torque equals I alpha. So I know that there is no other torque acting, just this. So therefore I can say that R times force of tension, where that's the radius of the pulley, right? There's no other radius, but I think I called it RP up there, equals I alpha. That is a Newton's second law expression for a rotating object. Does this make sense? This is exactly like writing sigma F equals MA, all right? Now I could keep on fleshing this out. I'm just trying to build some, I'm trying to use Newton's second law to build some equations, all right? So that I can start to solve for some of this unknown crack. Right there. So how can I be more specific over here? Well, this pulley is a disc, isn't it? Do I know what the rotational inertia of a disc is? Well, yeah, we've done that several times. I'm not going to do it now, but I can make a quick note that the I of a disc is 1/2 mr squared, is it not? Let me double, triple check I'm not lying to you, but I'm pretty sure that's what it is. Yes, for a disk, 1/2 mr squared. All right. So I can put that in right here for this I value, and this whole thing now becomes, and I can start to neaten this up. I have an R on both sides that can divide away. So I get that my force of tension equals 1/2 mr alpha. I know m, I know the radius of the pulley. If I could just figure out what the alpha is. I wonder if I could figure that out. So I know that this thing is going to be rotating this way. It's going to have an alpha. It's going to be speeding up its rotation that way, obviously, because this torque is pointing, this force is pointing down. All right. How can I figure out what the alpha is? Well, maybe I could recognize that I have a system of objects here, don't I? This mass, this little m, this box, is attached via the string to this object. So let's think about this. I know that right here, a little piece of rope right there is going to be accelerating downward. It's going to have some downward acceleration, some tangential acceleration, some translational acceleration. And that's got to be the same acceleration as this mass right here, doesn't it? So if I could figure out the acceleration of this mass somehow, then I may be able to figure out the acceleration, the angular acceleration of my pulley. Because think about it, a point right here having a downward acceleration, that's a tangential acceleration, isn't it? Do I have some idea or expression that relates tangential quantities to radial quantities? I sure do. I know that, I'm going to write it right up here, I know that A tan is equal to alpha r, where r is the distance away from the axis of rotation to that point. Well, that's just big R, isn't it? So I know that A tan, the tangential acceleration of this point here, which is equal to the acceleration of the rope, which is equal to the acceleration of my mass, has got to be equal to the angular acceleration of my pulley times big R, times the radius of the pulley. So if I can figure out what the acceleration of this object is, then I might be able to figure out the acceleration, the angular acceleration or the force of tension, etc., etc. In other words, I have two unknowns right now, force of tension and alpha, so I need two equations. And I'm recognizing that I have reached the end of the line. I've written everything I can write for my pulley, so I now need to start working on this object. And I recognize that there is a deep connection between the two. This object is going to be accelerating downward, and that acceleration is related to the angular acceleration of my pulley. Okay? So now that I've written second law rotational crap for this pulley, I can write it for my box. So I know that Newton's second law says that the sum of the forces equals ma. And I always wanted to think that the direction of acceleration is positive. Okay, so I'm going to say that mg minus ft equals ma. Yes? So right now I have two equations. I have this equation, which is describing, using Newton's second law, the motion of this object, and I have this equation using Newton's second law for rotation, describing the rotation of this object. So what I can do now is try to combine these equations. This is an expression for the tension force, so I could plug it in right here, couldn't I? So I could say that little mg minus 1/2 big M r alpha equals little m a. Now remember what we just got done discussing. This acceleration is the downward acceleration of this box, which is the tangential acceleration at this point on the pulley, which we've already said is r times alpha. So I can write this little mg minus 1/2 big M big R alpha equals little m. This A is big R alpha, isn't it? Right here. Remember, that's how you get from tangential quantities to angular quantities. You multiply the angular quantity by R. And now I have, and that is the radius of the pulley. Now I have one equation that only has one variable. I can rearrange this and solve for alpha, can't I? So I'm going to get mg equals, I'm just going to add this to both sides and factor out an alpha. Alpha times 1/2 big M R plus little m R. I'm going to get mg over 1/2 big M R plus little m R equals alpha. And now I can solve for alpha by just plugging the numbers in. Once I solve for alpha, of course I can solve for the acceleration, and I can solve for the tension force as well, which is everything that the question asked me for. So let's go ahead and plug and chug our numbers in. The little mass was 1.2, the big mass was 2.5, and R was 0.2. And when I do that, I get an alpha, which is the angular acceleration of my pulley wheel of 24. And remember, the unit for that is radians per second squared, just like translational acceleration is meters per second squared. I can now plug that in here and get my force of tension. And I'm getting a force of tension of 6 newtons. And then, of course, I know that the acceleration tangent of the point on the wheel right here, which is also the acceleration of my little m mass, right, is alpha times r. So 24 times 0.2 and that gets me 4.8. That's a tangential acceleration, so plain old meters per second squared. And that's it, my friends. So this may seem a little bit overwhelming with everything that we've written and all the concepts we have to keep straight, but it's really the exact same type of question that we've been doing all along. It's a Newton's law question, analyzing the motion of these objects, where we just begin by drawing free body diagrams. That's all we did. So I drew a free body diagram for the mass here. I drew a free body diagram for my wheel. Recognized I wasn't worried about any any forces acting on its center of mass to cause it to move translationally, but there was a force located away from the axis of rotation, and I recognized right away that that could be a torque to cause it to have this alpha. So the first thing I did was I wrote an expression for that torque, and then I recognized that that is the only torque acting on the object, so that has to equal I alpha. I realized that my pulley is like a thin disc, and discs have an I of 1/2 mr squared, so I plugged that in for I, and I eventually reached a dead end with this equation. So then I went to analyze my other object. Sigma F equals ma, just like this, where I want down to be positive because that's the direction of acceleration, and then I reached another dead end. But then I realized, wait a second, the acceleration of this object is going to be equal to, because this system is connected by a rope, it's got to be equal to the tangential acceleration of this point. And we know that the tangential quantities are related to the angular quantities by multiplying the angular quantity by the radius, or the distance away from the rotational axis that that point is, and that's r. So I was able to write this expression. That allowed me to go here. And then finally, I was able to just put one unknown, my alpha. Once I found alpha, I could find force of tension. And then, of course, I could also find the translational acceleration of the system. So really the only thing that we're adding is that on these free body diagrams for extended objects that may rotate, you actually have to draw out the object. Draw any forces acting on the center of mass. Any force acting on the center of mass of the object does have the capability of accelerating that object translationally. Any force acting at some distance away from the axis of rotation could provide a torque, causing the object to rotate. And that's really the only difference, is that now we are drawing extended bodies, free body diagrams for extended bodies of shape. We're worried about where the force is on the object compared to the axis of rotation, because it's going to provide a torque. And then, of course, one big key realization that may have been difficult for you, but now that you've seen it, hopefully you'll be able to do it in the future, is that the acceleration of this object showed up in this one as well, because it's the tangential acceleration at this point on the edge of the disk. Okay, so let's see. Let's say that we have a roll of fishing line, and us wacky physicists, we like to do wacky things. So we take the roll of fishing line and we tape the free end of the line right there to the ceiling. And here is the disc that comprises the roll of fishing line. It has a mass of m. It has a radius of r. And we just let it fall. We let the thing fall. So as it falls, it's unrolling, basically. And yeah, it's going to lose a little tiny bit of mass, but let's say that the mass of fishing line that, stays and unrolls from the spool is insignificant to the total mass of the spool, so we're not really worried about that. And let's say this is a thin disc, my spool of fishing line. And what do we know about thin discs? We know that their I value is 1/2 mr squared, so we're already thinking about that. So why don't we just redraw our disc, and here's what we should think about. I want to think about all the forces acting on the disk. All right. So what forces are acting on the disk right now? Well, I know that I have the force of gravity, and that is coming straight down from the disk's center of mass. And then I have like a tension force up, don't I? Right here. Okay, here is an important thing. Let's say that this cylinder, as it falls and it's unwinding, that it's unraveling from the string without slipping. Again, we're going to have a whole discussion about this, but this is important to know right now. When you see that something is like rolling without slipping, that means that the velocity of the center of mass of that object is going to be equal to the velocity tangent of the object, and the acceleration of the center of mass is going to be equal to the tangential acceleration of the object. So here's what this means. Like without slipping means that that a point at the edge is not moving faster and outpacing the middle. That's basically what it means. It means that the center of mass is moving with the edge. That's what it means to have no slippage. Again, we'll talk about that more in detail when we look at wheels rolling on surfaces. That'll probably be later this week. So if something is rolling without slipping, and this disc is unraveling from the fishing line without any slippage, then I know that right here, this point has got to be moving just exactly like the center of mass is moving. Okay, so hopefully that makes fairly good sense. So here's one question. We want to know what is the acceleration of the center of mass of the disk. All right. So here's where a lot of people screw up. They think that, oh, well, the force of gravity is the only force acting on the center of the object, so the acceleration must just be little g. But unfortunately, that is not the case. Because it is true that this tension force acting over here, even though it's not acting on the center of mass, it is still keeping the object from falling as quickly as it would, from accelerating as quickly as it would. In other words, it is still providing an upward tension force that is somewhat counteracting the downward force of gravity on this object, okay? In other words, it's going to have this motion downward exactly as if that tension force was right there in the middle. Okay? Now, of course, the tension force is not in the middle, so it has key issues for rotating because here's the axis of rotation, right? So it is significant that the force tension for rotation is significant for rotation, that the tension force is over here away from the axis of rotation, but it is not significant that the tension force is over here when it comes to translational acceleration. Okay? So if I want to know what is the acceleration here, I've got to recognize that the center of mass is accelerating with a point at the edge, with a point tangent, because it's rolling without slipping. And I know that acceleration tangent is equal to alpha times r. So if I can figure out what alpha is, then I may be able to figure out what the acceleration translationally is. Okay? So what I'm going to do now is derive an expression for the force of tension. I know that it is causing a torque. I know if I were to draw an r vector right there, right, from the point of application of the force to the axis of rotation, those are 90 degrees away from each other. So I can say that the torque is just equal to force of tension times R, right? And I know that the net torque, that's the only torque acting, because the force of gravity is not a torque because it's acting at the center of the object, is acting at the axis of rotation. In other words, if I were to consider force of gravity to be a torque, its R value, a vector drawn from the point of application to the axis of rotation, would have a value of 0. So the torque due to gravity is 0. But the tension force is located away from the axis of rotation, so it does provide a torque. Fr sine theta, where the sine of 90 degrees is 1, so Ft times R. And I know that equals I alpha, doesn't it? So Ftr equals I alpha. That's Newton's second law for torque. Sum of the torques equals I alpha. And of course it's a disk, so I know what the I value is. Force of tension times R equals 1/2 m R squared times alpha. All right. I can divide both sides by R and get an expression for force of tension. So force of tension is going to equal 1/2 m R alpha, just like that. All right. And now I can write a Newton's second law equation for the disk translationally, because that's what I'm trying to find, the translational acceleration of the thing. And I want down to be positive, because I know it's accelerating downward. So that Newton's second law equation is going to be the sum of the forces is ma. So the sum of the forces is going to be mg. That should be a big M, shouldn't it? Minus the force of tension, which I've already expressed right here. 1/2 mR alpha is going to equal, there's my net force. Force of gravity minus force of tension equals the mass times the acceleration, just like that. And I can rearrange this to solve for acceleration. I know that alpha is tied to the acceleration of the center of mass, which, because it's not slipping, is tied to the acceleration of a point tangent. These are accelerating together. All right. So this becomes A tan over R equals alpha. And I can plug that in right here, and then my only unknown will be A tan, or the acceleration of the disk as it falls, the translational acceleration, which is what the question is asking me to find. So I'm going to get mg minus 1/2 m R. Alpha is A tan over R equals ma. Just like that. And now I can solve this for A. Big mg minus 1/2 ma equals ma. Add 1/2 to both sides, I get big mg equals 3/2 ma. A is going to equal 2/3 g. So there is the acceleration of the thing translationally. Please note the key here, and this is going to come back to haunt us about 1,000,000 times, is that this is only true when an object is not slipping on the surface that it's rolling on. This is kind of abstract and wacky, but we can view this as if it is rolling on this surface, rolling on the line as the line unspools and unravels. It doesn't slip as it does that. In other words, everything kind of goes together. So a velocity of this point has got to equal the velocity of the center. The acceleration of this point has to equal the acceleration of the center. And that allowed me to basically combine these two equations. This is exactly the type of analysis you guys are going to have to get used to doing. I am analyzing the object extensionally. I'm looking at it in terms of what's happening to it based on where the forces are, and that is going to get me a torque analysis. And ultimately that got me here. And then I analyze the object again in terms of what's happening to it translationally. Just what are the forces like that could be affecting the object as a whole? In which case I collapse the object down to a point particle again, and I just assume that all those forces are acting on the center of mass, because they might as well be for their effects on translational motion, okay? So this free body diagram gets me torque, gets me Newton's second law for rotational stuff. This one is its equivalent, where I don't care that the force of tension is over here. I'm just saying that the force of tension is counteracting the downward force of gravity translationally. So yeah, it's like I'm treating the object like a point particle, and I'm saying that there's a force of tension up and a force of gravity down. I don't care at all where those forces are located, because I'm not worried about rotation for this part. I'm just worried about translational motion and how those forces interact translationally with each other. All right? And then once again, we recognize that without slipping, so we could write this statement, and that helped us replace the alpha in my force of tension. And again, we counted the force of tension as negative in this case, because I always want direction of acceleration to be positive. That allowed me to put my force of tension in terms of my overall translational acceleration, which is right here. And that was my only unknown then that I had. Okay. So then to figure out the force of tension, I can figure out what alpha is now. I have regular translational acceleration in terms of little g, 2/3 g. And I know that alpha is that divided by r. So I can say, therefore, that the force of tension is 1/2 mr. Alpha is a over r. So 2/3 r times g. And my r's are going to cancel out. And it looks like my 2's are going to cancel out, so it looks like I get mg over 3 is the force of tension. And that makes perfect sense, because if my downward acceleration is 2/3 g, then I need a 1/3 the force of gravity going up to counteract that and result in a downward acceleration of just 2/3 g instead of 3/3 g. All right. Okay, so big takeaways here. You should be thinking about what it means if something is rolling without slipping or is rotating without slipping. Then the velocities at the edges, the accelerations at the edges are going to be equal to what's happening at the centers. This equation right here gets me the tangential acceleration, but we've just said that that is also the translational acceleration of the whole thing. So that was a key. And of course, the biggest thing is drawing your free body diagrams, drawing one for rotation, where we care about where the forces are extensionally on the extended object with shape, and then drawing them, just pretending that the thing is a point particle to figure out the translational acceleration of the system. And then you just derive your equations. All right. You guys are going to be practicing this on your own, and tomorrow we will look at two things. We'll look at rotational energy, so energy with rotation, and we will look more carefully at objects that are moving across surfaces that are rolling. And we'll talk more in depth about what this whole slipping and not slipping thing is. All right, so you guys go forth and practice this torque stuff, and let me know if you have any questions. We will meet back to discuss it, I think on Wednesday. All right, best of luck.